Hello, welcome everyone to this new webinar. Today we want to cover reflexes. What we will cover today are the F wave, the H reflex and the blink reflex from a clinical point of view. First of all, this presentation are the opinions expressed by the speaker, not Natus Medical Incorporation. We do get those information from various guidelines available on the internet. However, they shall not be taken as a Natus statement. This webinar is part of a larger project we have within the company where we provide as a clinical application team various webinars covering specific modalities. You may attend some webinars on EMG, on IOM, on EEG, ICU and sleep, all presented by the clinical application specialists. If you want to retrieve all our recordings and if you want to get informed about our upcoming events, you can reach our clinical website www.natusneurologyacademy.com. About myself, my name is Anthony Milo. I have a bachelor's degree in biotechnology and biomedical engineering from Grenoble Institute of Technology. I entered Natus in 2011 as part of the application team in France, was covering our product lines in EEG, EMG, IOM on the field, and joined the international clinical application specialist team in 2016 to focus more on the EMG and IOM product lines for the region Europe, Middle East and Africa. You may find on this slide my email if you have any questions about the upcoming subject. So today what we want to discuss are the reflexes. Before we go into more details of F wave and H reflex and so on, we need to understand what a reflex is. So a reflex is an efferent response to an afferent stimulation. Those terms will be found in any clinical paper you may find on reflexes. Basically, it's also known as a reflex arc. What we mean by that is that you have an afferent segment that will transmit information proximally into the central nervous system. Transmission will be done there through synapses or interneurons or polysynaptic connections. And that information will go back to the peripheral system through the efferent limb. If you look at the picture on the right side, you can see, for example, a sensory stimulation that will go up to the spinal cord and through an interneuron transmission will elicitate a response from an alpha motor neuron going back to a muscle. This creates a design that looks like an arc, which is why we call it an arc of reflex. As mentioned previously, today we want to cover the F wave, the H reflex and the blink reflex. Let's start with the F wave. The F wave was named in 1950 by Matt Lattery and McDougall because it was first recorded from the intrinsic muscle of the foot, therefore F wave. It is basically like a motor nerve conduction study. However, we do record a longer duration. This will provide information about proximal segments of motor or mixed nerves, and it can be used on any motor and mixed nerves. It comes generally after we had already a motor study giving us information about distal segments of the nerves, and therefore will mainly focus on the proximal segments. F-wave are generally used in peripheral neuropathies, in Guillain-Barré syndromes, radiculopathies, proximal nerve lesions, spinal shock. Let's understand the method now. As I mentioned previously, this can be elicited from any motor or mixed nerve, should not be used on sensory nerves. What happens is we do stimulate a motor or mixed nerve supramaximally. The action potential will travel in two directions. One directly to the muscle, which will get us the motor response, and one will travel proximally to the spinal cord. Proximally, that potential will reach horn cells, which will backfire and produce a smaller motor response on a later latency, around 30 to 50 milliseconds. Basically, the F waves are those small motor responses that are appearing at this 30-50 milliseconds duration. The F wave test consists of a series of the small potentials. Therefore, we will have multiple stimulations to record multiple small responses. Out of those responses, we can calculate what is called the peripheral conduction time, as described by the Kimura formula, that takes into account the motor latency, the F latency, the duration it takes to backfire within the spinal cord. On the right side, you can see the different settings for the F wave. As you can see, we have a split sensitivity. We divide the sensitivity between the M response and the F response. The F response is so small compared to the M response that if we want to see both responses with the same sensitivity, one may not visualize the F response. Therefore, the sensitivity for the F wave is about 10 times more than the motor response. The stimulation intensity should be supramaximal to get a supramaximal motor response, and therefore the proper F wave. And we will do 10 to 15 stimulations at quite a low frequency. We can do it manually or at a low rate, around 1 Hz. Now, let's see what happens when we have a recording. Here is an example using the ulnar nerve. The stimulation electrodes and the recording electrodes are the same one than for a motor test, and the placement is also the same. In this example, we have a distal F response where the stimulator will be on the wrist and the recording on the ADM. So, to better describe what was said earlier about the bidirectional stimulation, one can see that when we stimulate, we have a first response going straight from the stimulator to the recording electrode, giving us the M response. The second direction takes the stimulus up to the spinal cord and then back into our ADM to have the indirect response called the F wave. Now, to have the complete study, we need to keep that supramaximal stimulation and record 10 to 15 sweeps with F response. The F response is not consistent. It may have different latencies, it may have different morphologies, which is absolutely normal because the connection to the motor neuron within the spinal cord may not be always the same for different stimulations. Out of those responses, we can have an F response present or absent, which then we call a block. For the data that will be recorded, typically we mark the shortest F response that corresponds to the fastest conducting fibers. A good way to be able to mark this shortest F response is to superimpose all our stimulations, which will show us better the onset of the response. In some other cases, an alternative is to mark every F response, and in this case what we want to record is the mean F response latency, which will represent the mean conduction fibers, and also will allow us to assess every single stimulation and assess the amount of blocking. Typically, one also records the F-M latency difference. And on top of that, we can have other parameters also recorded. The first one is the F amplitude, that will have a representation of the motor neuron excitability. We may also want to record the fiber density, and I will go into the details in a little while. And also we can calculate the persistence of the F wave, which is basically the percentage of F wave recorded out of all our stimulations. This will give us the percentage of blocking. The persistence calculation can only be done if we mark every single sweep in our recording. So in conclusion, we have two main types of data recorded from this kind of study. One will only take into account the shortest fibers, and in this case we can have the F latency, F-M latency, the velocity, or we can choose to take the time to assess every single stimulation, and out of this we can also have the F amplitude and the F persistence. When we have a healthy patient or an easy patient, we can stimulate 7 to 10 times. For more difficult patients, one may need to stimulate more, from 10 to 15 times. The calculation of the persistence only starts to be reliable once we have 10 stimulations. So for a patient with 7 stimulations, the persistence may not be taken as a valuable data recorded. About the velocity, we need to be extremely careful how we calculate the velocity. In the case of velocity, we want to have the nerve velocity between the site of stimulation and the spinal cord. So basically, the distance that we take into account as a user is the distance from the stimulation site to the spinal cord and back from the spinal cord to the stimulation site. So basically it's 2 times the limb length. For the upper limb, we can measure that length from the stimulation site to the spinal cord. However, most of the softwares take into account this back and forth distance, so they already do the multiplication by 2. In that case, in the software, the number we need to enter for the distance is the limb length, not the total distance. For lower limbs, however, the distance to the root or to the whole cell is difficult to measure. Therefore, there has been a consensus to take as a limb length the patient height times 0.8. In that case, in the software, what we need to enter as a distance is the patient height times 0.4. In some cases, when the F wave is difficult to record, there is a small trick we can use to facilitate the recording, which is called the Jurassic maneuver. Basically, if you want to record an F wave from the left arm of the patient, you may ask the patient to contract slightly the right side of his arm, or to contract the jaw, and this will facilitate the recording of an F wave. More generally, in reflexes, a slight contraction of the contralateral limb can facilitate the recording of a reflex. One thing that can happen when you do an F response is you may see in some recording a small response that is extremely stable with low amplitude, constant latency, constant morphology, showing before the F wave, also after, mainly before. This should not be mistaken with an F response. The small potential, as you can see with the green line on this slide, is called the A wave. Basically, this happens if the stimulation intensity is not at supramaximal level. In this case, we have only one branch of the axon that is excited, and when it goes up to the spinal cord, it will reach a point of branching, and instead of going to the spinal cord, it will turn to the second axon and go back to the muscle. This is why we will have always a constant latency and a constant morphology into this response. Again, this is not an F response, and it should not be mistaken with an F response. We usually don't see this in healthy patients. So if you see this kind of response, either it can be pathological, or you may not have reached the supramaximal level and you need to increase the stimulation intensity a little bit. Moving on to the H reflex. The H reflex is named after Paul Hoffman, who has described this technique in 1910. This provides information on proximal nerve segments by stimulating this time the sensory fibers. As you can see on the picture on the right, the difference between the F wave and the H reflex is the connection network done in the central nervous system. In one case, in the F wave, we go directly to a horn cell that will bring back the information into the muscle. In the case of H reflex, this time we stimulate sensory fibers that will then go inside the spinal cord through interneurons and bring back the response on the muscle. This kind of technique is used in polyneuropathies, in radiculopathies, mainly on S1, but there are also options for L2, 3, 4, C6 and 7, and it's also used for upper motor neuron lesions. The H reflex cannot be performed on any kind of nerves and muscles. There are a few muscles that are mainly recorded. Probably what we see mainly is the soleus muscle. However, there are other muscles existing. And this is based on increasing stimulation from 0 milliamp to supramaximal stimulation. Just like in the F wave, once we stimulate a nerve, the stimulation will travel bidirectionally, and the process used in the H reflex can be described in 3 stages: motion H, motion MH, and motion M. In the motion H, we have a stimulation level that is fairly low, just above the sensory threshold. In that case, the sensory fibers are stimulated but not the motor fibers. In such case, the sensory stimulation will go up to the spinal cord, go through the interneuron, connect to an alpha motor neuron, and go back into the muscle. If we increase the intensity, we will go to the second stage. In that case, we will be above the motor threshold and above the sensory threshold. In that case, the sensory stimulation may collide with the motor stimulation elicited at the same time, collide and decrease the response from the sensory stimulation. In that case, we will see a motor response starting to appear because we are above the motor threshold, At the same time, the reflex due to the sensory stimulation will decrease due to that collision. As we increase the stimulation level more and more, we will have also enhanced collision between the motor and the sensory stimulations. Up to the level where we will have a total collision, so our reflex response will disappear and our motor response will maximize. So what we want to record are the two maximal responses, the maximal M response and the maximal H response, that both appear at different stimulation level. In terms of settings, this slide provides you the optimal filters for such recording. The stimulation current should be of very fine precision. We should be able to have a very thin stimulus resolution. The stimulus duration is quite high, 1 millisecond, and the stimulus frequency is manual. Although we say manual, we need to respect a certain stimulus frequency that has to be extremely low, around 0.3 Hz, which means around one stimulus every 3 seconds, so that we can avoid reflex habituation and therefore a decrease in the amplitude of our reflex response. In any case, even if you want to go a little higher frequency, we shall not exceed 1 Hz. For the stimulator, we shall place the stimulator cathode proximally so that we can avoid any anodal block. Let's make our explanation a little more understandable using a graph. Here you can see the H test performed on the tibial nerve with recording adhesive electrodes placed over the lower limb and the stimulator around the popliteal. We have here a mixed nerve with the sensory nerve and the motor nerve. At a very low level of stimulation, on the first stage, when we stimulate, we have only the sensory fibers that are stimulated. In that case, the stimulation goes up to the spinal cord, makes the connection through the interneuron, and goes back into the muscle, eliciting an H response. As we increase the stimulation, we will reach the stage where we have H and M motion. In that case, both type of fibers are stimulated, and we have a collision between the efferent information from the motor nerve and the sensory reflex. As we can see on the right side, we start to see a motor response, and we have a decreased H response due to the collision. If we increase the stimulation even more, we will start having a total collision, and in that case, only the motor response will be seen. We have a total collision, and only the motor response is showing. So when we record our H test, we need to start at very low intensity and increase time after time. When we reach the sensory threshold, we start seeing an H response, which increases until we reach the motor threshold. Then we have a small motor response, and the H response amplitude will start to decrease. And as you can see, when we look from the top to the bottom of this graph, as the motor response increases, the H response decreases up to the point where we have a total collision and only the M response amplitude increases. From those waveforms, we save the waveform with the maximal H response and the maximal M response. In a daily praxis, first of all, we need to find the perfect stimulation point by recording a motor response. Then we set our stimulator to 0 mA and increase the current by very low steps, 0.02 mA roughly, until we reach the H sensory threshold, and then we continue until we can record the maximal amplitude for our H response. After we reach the maximal H response, we can increase the current by bigger steps of roughly 1 mA until we reach our supramaximal motor response. We save the sweep with the highest H response and the one with the highest M response. The data we will then save for the diagnosis are the H latency for the maximal H response, the maximal H amplitude. We will record the ratio between the M and the H amplitudes, called MH ratio, that will assess the axonal degeneration and also help visualizing side-by-side asymmetry. And one may also want to record the H index. You can see on the slide the formula. This is an index that can be helpful because when you talk about latencies, for example, patients have different height and different limb length. So by only taking into account a latency, you may get distracted in your values by the limb length. The H index takes into account the patient height and therefore provides you an index that is not influenced by patient height, and that might help when you do multiple patients. This technique is mainly known to be performed on the soleus for S1 radiculopathies, but it may be used on other muscles, especially if we consider using the Jędrusik maneuver. So the reflex with a patient completely at rest are present on the tibial nerve using the soleus muscle for this S1 radiculopathies, but may also be performed on the femoral nerve and the median nerve using the quadriceps and the flexor carpi radialis for different spinal cord segments. Other muscles can also be recorded, but will be extremely difficult to get if the patient is at rest. And by using the Jędrusik maneuver, we may be able to record H responses for different range of nerves, for example the radial nerve, the median nerve, the peroneal nerve, for supplementary segment of the spinal cord. Studies have been performed on another array of muscles where it was said to be extremely difficult to get an H response despite this Jędrusik maneuver. So this table here provides you the muscles where it was written we could get an H response fairly easily with patient at rest or patients slightly contracted. Moving on to the blink reflex. The blink reflex is the last reflex that we will cover today and was a test that was described by Kugelberg in 1952. This is a test that will assess the 5th and the 7th cranial nerves, so the trigeminal and the facial nerves. This will be used mainly for facial paralysis, as an example in Bell's palsy, in lesions in the 5th or the 7th nerve, hemifacial spasm, acoustic neuroma, and polyneuropathies. the difference between the blink reflex and the other reflexes we have discussed until now is that in the case of the blink reflex, there is one method that exists in terms of stimulation and recording, where the other tests can be performed on an array of nerves. And in that case, here for the blink reflex, we can really go into the detail of electrode placements and so on. In the case of the blink reflex, we do stimulate the supraorbital nerve, which is a sensory nerve that is derived from the fifth nerve. That stimulation will reach the brainstem, and through an array of connections will reach the orbicularis oculi muscles on both sides of the patient. So in this case, we have a stimulation on one side of the patient and a recording bilaterally. You can see below in the picture the connection made in the brainstem. We only display the response on the ipsilateral side to simplify this picture. But as you can see, we have a stimulation on the supraorbital nerve, basically above the eye. It will reach the brainstem and then have two connections, one going to the ipsilateral eye, the other one going to the contralateral eye. And that nerve, the facial nerve, will reach the orbicularis oculi. So in this case, the efferent nerve is the trigeminal and the afferent is the facial motor nerve. Out of this stimulation, we record two channels, one on the ipsilateral side, one on the contralateral side, and we'll record two responses called R1 and R2. R1 is a direct response to the stimulation and therefore will be only seen on the ipsilateral side of the patient. The process to get to the R1 is a desynaptic pathway between the main sensory nucleus of the trigeminal nerve and the ipsilateral facial nucleus. The R2 can be seen on the ipsilateral side and the contralateral side, and this is our indirect response. This R2 is due to polysynaptic connections between the spinal nucleus and bilateral facial nuclei. In terms of settings, we do have quite a short duration for the current stimulation, that is 0.1 milliseconds, and a stimulus frequency that will be manual. We don't want the patient to expect the stimulation to make sure there is no muscle contraction due to the expectation of a stimulation. 0.1 millisecond duration is painless for the patient, but in some cases it can be difficult to obtain responses. So if you have a patient where you cannot record proper responses with 0.1 millisecond duration, then you may increase the stimulus duration. In some universities, facilitation of the recording is done by using a short train of stimulation instead of a single pulse. Basically, what they do is they have a short train of 3 pulses with 0.1 millisecond duration and a very high frequency in the train. Regarding the positioning of the electrodes, the active electrode can be placed on the lateral part of each eye, and the reference will be placed 2 centimeters below. One may use adhesive electrodes or cup electrodes to do the recording. The ground will be placed medially on the nose or the chin. One may also use a different active electrode position where the active would be placed right below the eye, and the reference electrode once again 2-3 centimeters below. The stimulator will be placed with the cathode over the supraorbital notch, which we can feel if we pass our finger over our eyebrow. We can feel one placement with a little cavity and a slight pain. That's where we need to place the cathode of our stimulator and the anode above on the forehead. Once we have this proper positioning, we can record our sweeps, one time on the left side of the patient and one side on the right side of the patient. We have bilateral recording with ipsilateral side and contralateral side. Ipsilateral side showing us R1 and R2 response, and the contralateral side showing us the R2 response. To make sure we have the proper placement for our markers, the stimulation needs to be repeated at least 3 times per side. For blink reflex, there are normative values that I provide you in this slide. There are normative values for R1 and R2 on each side of the patient, but also what will be important is the difference of latency side by side. So for example, the difference of latency for the R1 between the right side and the left side of stimulation has to be below 1.2 milliseconds. And for the R2 response, the difference between the ipsilateral side and the contralateral side should be below 5 milliseconds. Clinical papers also provide a range of amplitude for R1 and R2 in patients. However, the amplitude is always said to greatly vary between patients. The main focus is done on latencies more than amplitude. Now, what will be the effect on the diagnosis when we take into account the delays of R1 and R2? If R1 has a delay or there is simply an absence of R1, we know that there will be a disturbance of the 5th nerve or the 7th nerve, or both, on that stimulation side. So if you have an R1 absence when you stimulate on the left side, you have a nerve lesion on the left side. The R2 response and its delay or attenuation will help make the difference between a lesion on the 5th or the 7th nerve. So if you have a trigeminal nerve lesion, there will be an R2 delay and or attenuation when the affected side is stimulated. If you have a facial nerve lesion, the R2 will be delayed on the affected side recorded, no matter what side of the patient is stimulated. There is one small pitfall with the blink reflex, that is the stimulus artifact. If you have a high stimulus artifact, you may want to rotate the stimulator around the cathode. However, unlike the nerve conduction studies where we may rotate the stimulator up to 90 degrees, we need in this case to be careful not to turn too much. Because if we stimulate with a too high angle, we might stimulate the contralateral supraorbital nerve and therefore elicitate 2 R1 responses. So R1 responses on both sides of the patient, which makes no clinical sense. So if you have a recording with 2 R1 responses, the position of your stimulator is wrong and you turned it too much. So I hope these explanations have provided you a good overview of reflexes in EMG studies, that it helps you better make the difference between the different tests and how we may use them. If you want to retrieve this video and also get access to the presentation, you may want to reach our clinical website, and if you have any questions, you can contact me on my email provided here on this slide.